Educated India.
So we'll get back to what I'm comfortable. An example. out of all of this is a good illustration, and our afternoon very basic calculations, but just focus on the details. This is in reinforced concrete. So the building is let me see. So the building is a 6-story building, and it is a ordinary concrete moment frame. Again, I showed you several occupancy categories. Occupancy category is 2. So the building plan is got 2 bays in the y direction and 9. So let's equal 1, 2, 3, 4, 5, 6, 7, 8. So that's 9 bays, 1 in the X, and then there is an cantilever canopy here on either side. So the overall length is, the canopy is 6.5 feet. We have canopies up to 8 feet, 10 feet, maybe the outer range, but this is a standard. And here this is 9 at 24 feet center to center, and here you have 2 bays at 36, I think it is 36.5. feet. Let me check that. These are cantilevers. There are columns and joists. The joists or beams are 2 of them. Oh. So there are 2 of them. These are 3 feet apart. So 3 feet on centers, beams, and there are openings. So in the third bay there is a half opening, then there is a full opening in the 5th. So these are openings, and 6th, 7th, 8th one again a half opening. The data given is story height. We spell story there as S-T-O-R-Y. I think here you may have it as S-T-O-R-E-Y. Either way, story height, color and color. If I write C-O-L-O-U-R there, I'll get corrected. Autocorrect to C-O-L-O-R. So 12 feet, first story is 13 feet, and there are 3 openings for stairwell and elevators, 1 stairwell and 2 elevators. Then other information pertaining to the slab is it's a 4-inch thick slab with reinforcement of 0.87 square inch per foot in the longitudinal direction and 0.14 square inch per foot in the lateral or transverse direction. Given that the materials are Fc prime, which is FCK 3 KSI, and Fy is 60 KSI, and there are columns. So this is say T1, then there is the interior, let's say interior T3 and an edge column T2. So the columns are 24 inches by 24, just for this example, 24 inches by 24. We had type 1 or T1 is an edge, which is these reinforcement details are provided. These are your normal design reinforcements. In concrete, there are some guidelines. I talked about your Fc prime should be between 3 and 10. Fy, the reinforcement should be less than number 11. Number 11 is not exactly 11 by 8 inches, but it is close to that. Type 2 is a column with 6 number 11s. So, and type 3 is a column with 8 number 11s. So these are the data provided. Question is to design the peripheral, internal, vertical and around openings peripheral ties. It's a fairly straightforward problem, but we'll just go through all the details. This will be part of the tutorials this afternoon. So first step you would do here is from UFC 4-023 problem, you gather the following data. So we have the directions defined as so this is your longitudinal and let's say that's your transverse. So other information is the overstrength factor is omega is 1.25, and then you also have the strength reduction factor is 0.75. For now, take this data as needed. Then from the problem itself, we have length of the bay, LL is the same, is 24 feet. So, this is 24 feet and the width of bay here LT is given to be 30, yeah, I thought it is 35.5, that is what I was wondering, hesitating. I think I have taken it as 35.5. Unless I have been inconsistent, if I have, I will let you know, but so the area of the building, no, wait, I think I have been inconsistent. So, this is still 36.5, sorry about that. So, the area of the building is 9 times 24 plus 2 times 6.5 and multiplied by your 73 feet. Beam dimensions are given, it's a 4-inch slab and the beam itself is, this is the dimensions of primary beams between columns. So, this is for self weight purposes. So, we start with our second step, which is to calculate the dead and live loads. Several things we account for, I am sure you do that here also, is the dead load to what we call as mechanical, electrical and plumbing. All these so the mechanical, electrical, plumbing is 10, we consider 10 pounds per square foot, and then the wall is 20 pounds per square foot for a brick wall. So, the height and the span are the other variables, the thickness is accounted for there. So, the total dead load is the dead load due to MEP plus the dead load due to cladding plus the dead load due to the slab and the beams and the dead load due to columns. Now, here we will consider these three. So, no, the MEP is 10, the cladding is 20, and I have not shown the calculations here, but the slab and the beam, if you take center to center of 4 feet or 3 feet and take the area, multiply. So, the density of concrete we consider 145 to 150. So, 150 reinforced is taken as 150. So, that reduces to 127 here if you pounds per square foot comes to 173. Let us not worry about all the details of those calculations, but basically you calculate that value. You can take the weight and distribute it over the area and get the PSF equivalent PSF. The live load itself is typical buildings live load is, especially classrooms like this, for us would be 50 pounds per square foot. and partitions. So, this is live load plus partition live loads. In our case, it would be 50 plus 20 or 70 PSF. So, when we look at the factored load combination, we saw from the PowerPoint the load to be calculated WF is 1.2 dead load plus 0.5 live load. So, comes to 1.2 times 173 plus 0.5 times 70 is total WF per floor is 239.4 pounds per floor. So, any questions so far? Just collection of a lot of data so far. Now, we will start the tie design. We start with our internal tie force. And two categories, longitudinal ties, again these are internal. So, L1, which is LL, is 24 feet. We have seen LL is 24 and LT is based on the longitudinal directions. So, the force F1 is given as 3 WF LL. So, this is from the UFs, from again the PowerPoint. So, 3 WFLL is 3 times 239.4 pounds per square feet multiplied by 24 feet. So, comes to 17.23 kips per foot. And so, the steel area required, this is additional steel, it goes on F is equal to AS, assuming the steel yields. At that force, which in catenary action it will, multiplied by the overstrength factor. So, the 1.25 accounts for overstrength in steel or overstrength in concrete. We had talked about that earlier on. So, from here you can calculate AST is equal to F. Of course, multiplied by this is your overstrength factor of materials. In fact, and this is your strength reduction factor. In fact, there is even a limit on the overstrength. In concrete, for example, the overstrength is restricted to no, in steel itself, even the overstrength is restricted to about 18 KSI. So, if your strength of steel is 50 KSI or 60 KSI in this case, you can't have actual strength when you test it to be over 78 KSI. So, the strength reduction factor is phi. So, you have here phi F divided by phi times omega Fy. So, the force is, this is so many kips per foot, 17.23 by 12 kips per inch, and divided by 0.75 and 1.25 multiplied by Fy is 60. So, pretty basic. Essentially, a number 4 bar, that is a ½ inch diameter, that is a 12 mm bar. 12 mm bar is 0.2. So, basically you are saying 12 mm bar at 3/4 of an inch, no, half, 1.5, so 2/3, so 8 inches center to center, so to speak. But you don't, let's not worry about that. What you, the spacing should be less than 0.2 LT. So, this is 0.2 times, if you provide 1 or 2 bars, that is why this is, the spacing is restricted. So, this is 7 feet center to center. So, this was a longitudinal tie. So, what we have is provide outside the beams 0.31 square inch per foot outside the beam width, or then the next one is an internal tie. These are in each slab. So, the internal tie now, this is transverse. So, L1 is LT is 36.5 feet, and FT, the force is again the same as before, 3 WF L1. So, 3 times 239.4, I do not know if my math is correct, but this is 36, my calculations are right, maybe slightly off. How much is that? 25.4 or let us take it to be what I have. It may be slightly off, does not matter. 25.4, I have that value, kips per foot. And the spacing for the transverse tie is 0.2. Now, opposite LL is 0.2 times 24, which is 12 feet. So, you can provide what they are saying is you can, what is it? No, okay. What you can provide, I mean, that seems to be quite a bit. Basically, if you provide 2 of them, what they are saying there is, let us say this is your beam. If you are providing 2 of them, you should provide within 12 feet. No, 0.2 times 24 is 1.2. 24, 12.2, 1.2, this is 35.5, that is 7. So, you are providing the longitudinal ties within 1.2 feet, and in this direction within 7 feet. This is within each slab. So, you do not need to provide throughout, you can provide it within this outer range. And the area of steel is Ft divided by phi times omega Fy, or 24.21, a lot of repetitive calculations here, 0.75 times 1.25 times 60. So AST is 0.45. So there is more, there's more steel basically because the length, the span is 36.5 as opposed to 24. Then we look at peripheral ties. So over the edges we have brick wall weight. So we need to consider the brick wall weight. Now again, if you can help me with this, the partition weight, okay, I don't, I think I am okay. So partition weight is basically the wall weights, and this was included at 20 pounds per square foot. Those are the partition loads. So what we will do first is to remove the partition load from total load, which is in PSF. So this is 239.4 minus 20 PSF. Sorry, minus that had a factored, so 20 PSF times 1.2. So value here is 215.2 because we will add it back in a slightly different way. The wall weight, now this is as a distributed load. So the wall weight is 20 PSF multiplied by 1.2. And the height of the building or height of the floor multiplied by the span of the floor beam comes to 6.91 kips. The total weight is can be taken to be, so the total FP is 6 WF, this is the equation that I showed earlier on, plus 3 times the weight of the cladding. So comes to 6 times 215.2 PSF. LP, we have said this is spread over 3 feet, over 1 meter. So L1 is 24 feet, this is 3 feet plus 3 times 6.91 kips. That is why it was, the wall weight was separated for peripheral ties. So all of it comes to 102.2 kips. And so the AST is F sub P divided by same thing, So 102.2 kips divided by 0.75 comes to 0.56 square inches per foot. You can detail it, but we won't do it in this. But this is provided over 3.3 feet outside the beam. Outside the beam width, basically 1 meter. Then the second thing is the transverse peripheral tie. The load calculation is the same. And so L1 is LT, which is 36.5, and the cladding, if you can just help me with this number please, 1.2 times 20 PSF times 12 times 36.5. So this should come, it's about 10 point something, 10.5. Thank you. FP, again hold that number. So this, the total, this is FP is 6 WF L1 LP plus 3 WC. So 6 times 215.2 multiplied by, now L1 is 36.5, but the is 3 point, it's 1 meter, I should have, this is also 3.3. So 3.3 feet plus, it's kind of strange they have that over a meter rather than feet, but that's the way they have framed it. So this is 10.5 kips. Overall it shouldn't affect, what do we get here? This is divided by 1000, should be around 180 something. 180? So 6 times 25.5 times 36.5 times 3.3 by 1000 plus 30. 155 you said? Is that what you said, Raghav? Or who said that? 155 point? So 155, yeah, I thought it was a little bit higher. So, and then AST is 187.45 kips divided by is 0.98. So what you're providing is, if we look at, let's say, in this and in this region, and then let me change it to another color here. So in this is outside. So here you're providing 0.98 square inch per foot. All of these are 1 meter. or 3.3 feet, and here in the other one it is 0.56 per foot. So total steel you will provide is multiply by 3.3 and then give the spacing. So that's the peripheral ties to ensure that the slab has catenary action. You can ask the question, how about, are you going to overlap internal ties and the peripheral ties for the outer bays? You can provide the internal ties for the internal bays. So if you're having, here of course you have only one bay on that direction. So the internal ties can be provided here and here. And here and here. You don't need to double the peripheral ties and the internal ties. Then next one is the peripheral ties for openings. There are two types of openings, so we'll look at both of them. So, the first opening dimension is given, this is given here for the stairwell as this is the smaller opening, 8.8 feet and 15.7. This is for the elevator opening. And then the other one is clear opening is 21.8 feet and 33.2 feet. This is the stairwell opening. If we assume cladding over each opening, then the force for design of ties is Fp, which is 6 Wf L1 Lp plus 3 Wc. So 6 times 215.4 L1 multiplied, this is 3.3 feet plus 3 times the cladding, this is 12 feet height multiplied by L1. So L1 is the direction in which we are providing. So you will be providing the around here. So you will be providing around here, here. So L1 is, we are just taking the L1 to be that one. So 12 times L1. And so this is 20 PSF. So divide all of it by 1000. This is in PSF. So dividing the whole thing by 1000 comes to approximately 5.0 L1 kips per foot. And AST is FP by 0.75 multiplied by here LP. This is the total area over 3.3 feet. That's why we include it here. So this is in kips per inch. So this is let's see, this is in kips per foot, so kips per inch. So you have to divide this by, these are all in feet, pounds per square feet, pounds per square feet. So L1 is in feet and LP is in feet. So this is per square foot. You have to divide this by square inches. So you can say this is, can you just multiply, no, I think 1200, 3600 plus 36 times 20, yeah, I think this is 5,000 kips per foot, right? So you need to convert it into inches. So be consistent in the units. So this comes to AST, or you can take off the LP here. That would still be kips per, you need LP here. So this will give you so many square inches per foot. Yeah, Fy. Now just thinking about making sure the units are correct. So if you see, this is kips per foot. So this is feet and KSI. So this will become square inches per foot. Yeah, so this equation is correct. So AST is 5 kips per foot L1 divided by 0.75 times 1.25 times 60 KSI multiplied by 3.3 feet comes to 0.027 L1. Here it is L1 in feet, and here also L1 in feet. So you can have a little table drawn with 1, 2, 3, 4. I have four different values of L1, 15.7 feet, 8. This is for the first two peripheries. The second one FP is 79.4. This is in kips, 44.5, and AST in square inches per foot is 0.424. all of them, and you can provide it, provide over 3.3 feet on either side of the opening. All of them, as you see, is prescriptive, no calculations. The last one is vertical tie design. For the corner columns, you have different tributary areas. The corner columns will have only a quarter on either side. So, this is your breakdown, and the end columns you will have a larger tributary area. So, that is your interior columns. So, corner columns, the tributary area is 364.2 square feet, whereas the interior column, it is 846. The required tension forces are FV, first of all, is A tributary multiplied by WF, which is for the corner you have 364.2 multiplied by 239.4 comes to 87 kips, and the interior comes to 846, same thing, 846 multiplied by 239.4, which is 202 kips. And AST is FV divided by phi omega Fy. Phi and omega still remain the same. So, this is Fv divided by 0.75. So, what we get is, and thing to note here is, for the corner you get AST is equal to 1.54. For the, you can interior, you get 3.59, and you've already provided 4 number 11s, 8 number 11s. These are adequate. So, there is no additional for the given for the forces. No additional reinforcement needed. These are in tension. Typically, your reinforcement is acting in compression. So, when called into, when this tie action comes into play, these are pulled apart. Tension, this corner gets, so your column reinforcement in tension now. So, ensure continuity, full continuity. That's the main thing you have to do here. You can use mechanical splices. Well, if the rods are weldable, you can weld it. We would recommend using not just splicing. Splicing really, splicing works for compression, for transfer by additional things you might have to do here is mechanical splices, or if you provide additional reinforcement, you provide it. Using regular reinforcement, you can leave it. Additional reinforcement, you can provide this way, whichever you decide. So, that, and any questions? Things are pretty straightforward, but if you have any questions, I'll take them. What's that? You're mentioning?
Mitigating solutions also can be installed from this UFC document.
This UFC document is for progressive collapse guidelines. So, when you're talking of mitigating, you have other documents for that. You might most likely go to research. There's no UFC type document for mitigating purposes. When you talk of mitigating, what?
Already existing structures are there. We want to avoid progressive collapse.
Yeah. Yeah, if you have an existing structure, then you'll have to find a way to provide continuity. Maybe you are adding some kind of external plates for that purpose, all the way from the top to the bottom. Yeah, these are for newer structures. If you're having an existing slab already, right? And I know, for example, you have a, let's say this is your slab, and then you have columns in between. And so you can add the ties are in tension. If it is existing, maybe you have some kind of a wrap around here, FRP wrap, for example. Yeah. What's that? Retrofitting. Yeah. So FRP wrap, fiber reinforced, can go around in this manner. So that is one retrofit option. There could be other retrofit options as well. Clearly, it's going to be impractical to dig up any or core any concrete and put something on top. I mean, that's the main option I can think of. They do this even in regular flat slabs, for example, to enhance the shear strength. I'd look into what are the things they do in enhancing the shear strength of materials, and use the similar principles very similar to that. These FRP wraps works very well in tension. Even in columns, you could consider wrapping the entire column with FRP wraps, FRP sheets basically. Anybody's got experience in that? And you were saying, you were mentioning something? So yeah, they will have a adhesive. So you paint an adhesive and then you lay it on the floor. You can, yeah. And these are very thin wraps also. They are not very thick. So it will clear floor, it will create some floor discontinuities. So that is a finish that you have to take care of, find out ways to do it. Anybody else can think of or experienced anything else
Arm strengthening
with fiber reinforced?
no, the normal
Normal. So you add additional
additional
concrete around it, and then yeah. It will be too expensive also to put. You have composite columns with steel jackets, steel around enclosed. Yeah, that will be but expensive to do. Quite unnecessary. You don't need that kind of retrofit. Continuity is the most important thing. One additional topic. It's a very brief introduction to this topic, so we'll just touch upon this. Is glazing, because it's a very critical topic, and there are, I think, Raghav's group, Professor Painiyappan's group, there are people working, or they have done testing, so you can talk to them more about it. We'll briefly touch upon the materials. These are charts based on TM15, what is known as TM5 1300. It's an old document. You may not find it on the web. Maybe somewhere on the dark web there must be something there. And these are chart-based design procedures. This is old, so the data is also old. If you are using for special purposes, quite often they will go get it tested. There are chart-based design. Alternative is manufacturer-based specifications. For example, I don't know how it is here in India. In the US, if you are designing for bar joists, right, you've seen those trusses with bars. Those are not, they are code based, but most of your design are based on manuals that your specific manufacturer provides, and then so you go off of that. They have to conform to the code, so they provide the manuals based on code requirements, but you don't design per code itself. Typically, nowadays doors also I know there's a lot of testing that has been done. Typically, you have security windows. Security windows are designed to resist three things. You are looking at forced entry. It should be ballistic resistant. So this is bullets or any impact. So let's call this FEN. And so there are three different traditional windows. These are security windows. If you look at traditional windows, not security windows, these resist wind pressure and impact due to debris, wind debris. The design is based on you have for typically windows on the first floor or the ground floor here, so let me call it the ground floor. Based on the level of protection for forced entry, or ballistic resistance, this is BR, and blast resistance. Glazing types, you have several types that are used. One is annealed glass, basically heat treated glass is one. The annealing is in cooling form. Then you have heat treatment, and you have tempered glass. All of these are vendor specific. Look up the vendors for and what is available now here locally. You can use film to upgrade your shatter resistance. The glass that you have, there is no, and not that I am aware of, very specific design. The films itself, they ensure integrity of the glass. I have seen in special applications, if you are protecting equipment and things like that, to have a catch cloth or something like that right behind. Annealed, some basic properties or features of these types of glasses. Annealed glass is breakable into small pieces. And these become projectile. So annealed glass can cause fatalities or injuries. Of course, it is low cost, and other features of it is easy to cut. So you can use annealed glass if you want with, so use with film because it is low cost. Then you start getting into heat treated glass. Some of the properties, physical properties, are as follows. It has a higher breakage resistance. Strength is 2 times stronger than annealed glass. Here it is small pieces, but this heat treated breaks into shards, larger pieces. It's not fire resistant. It is expensive compared to annealed glass and cannot be cut easily. This is easy to cut, not easy to cut. So you have to treat the glass to the size that you desire. Then finally, tempered glass. This is the best form because to begin with it has 4 times the strength of annealed glass. The first one this glass breaks into cubical pieces. Of the three most expensive of, and again cannot be. Here in this case is that the first one is not easy to, or even cannot, you can even say this cannot be cut to size, cannot be cut. So, the fundamental principles given some of these types of glasses, the principles in glazing design, I used to work sort of a finite element analyst for a glazing contractor. So, we've done staircases for stadium and things like that. So, they do a lot of analysis. Glazing design is elastic behavior, completely elastic behavior. So, it's easy to do, not easy, it's the finite element analysis is the right approach predictive wise. You use multiple layers of glass. Then multiple layers of glass to bond them with glue, and then you could have a frangible sacrificial layer on the blast side. You could have it bonded to an inner polycarbonate type of glass layer in the forced entry ballistic type, ballistic resistance situations. In our application, in blast applications, a monolithic tempered glass is often used, is recommended. So, here is a brief table on 1, 2, 3, 4, 1. The properties of glass, the type of glazing, this max stress in KSI, the elastic modulus again in KSI, and Poisson's ratio. I have mentioned the Poisson's ratio because it is important when you use finite element analysis for glass design. So, annealed is in the range of 4.5. This is 10,000. This is, let us say, in PSI. So, 10 into 10 power 6 PSI, and Poisson's ratio is 0.22. If you have semi-tempered to or tempered, it is in the range of 7.5 to 16 KSI. To tempered and polycarbonates is about 9.5 ksi. These all have a similar elastic modulus. Polycarbonate is 35 into its lower not a whole lot of things. A common usage is laminated glass, where you have layers, multiple layers, and then in the center so this is say bond by polyvinyl butyrate PVB interlayer film. They are very thin films that can be utilized. We classify glass brick by, so the classification of glass, let us say damage. Methodologies have been developed, and let us say this is a room and you have a glass layer window here. And bless you, you have your blast load. So, it is classified into three regions. The first region is if it is within 3.3 feet. Then let us say this is a 10 feet room, 6.7 and 2 feet above the wall. So, let us say this is, so these are some classification levels. So, the protection levels are defined as follows. 1 is safe, and no glazing damage. Second is very high, glazing cracks. So, if you are a glazing manufacturer, you are looking, you can classify under, but retained in the frame. That is why a lot of times the boundary conditions make it, how you, the bites, how you design the bites make a big difference. The boundary conditions is very critical in these designs. Retained on the frame. Then the third one is high. The protection level in this case is none, again none, this is a low protection level. Now, glazing cracks, so 3 is, or 3A I should say, that is why this is 3A, this is protection level. Glazing cracks or glazing fragments, but falls within 3.3 feet with 1 meter of the window. So that's protection level. Then 3B is the next protection level. This is also high protection level. This is low. Now the 6.7 is basically saying glazing cracks and fragments fall within 10 feet. Of the window. Fourth, the protection, these are all protection levels. Medium, the protection level is medium. Now glazing cracks but falls so this is 3, I should say 4. So this is within 10 feet of the window, and within 10 feet of window, from window, but within 2 feet height from the floor. And the last category is, this is fifth category, is this is very low protection. You have here greater than 10 feet, greater than 2 feet from window and above ground. So very a variety. Now design wise, there are multiple design ways. I'll just show you one of them and how it looks like. So if I were to import an image, if I can, yeah. It's an old document. I don't know if you can see it very well, but if you see here, this is showing peak blast pressure on and here you have duration of, so you still have PR versus TD. So once you determine what it is, goes, as you see, this goes up to 35, 20, 35, it depends. T is, there are two ratios here, A by B. This is the window dimension. So say this is 12 inches and 48 inches. So A by B is equal to 4. And here it is the thickness of the glass. So designs, these are for different, available for different types of glasses. So when you look for manufacturers, see if they have, or you should look for data that gives pressure versus time. This is time in milliseconds, and these are curves that tell you how much it can withstand Now this is, if this is 12 by 48 for example, although A by B is 4, there are both are A by B of 4, but this one gives 12 by 48. So this is a 12 by 48, so this is the glass size, and the value here 9 point, it tells you in PSI. So let's say given PR equal to 10 PSI and TD is 20 milliseconds. So PR is 10 and TD is 20 right here. And the thickness is half an inch. And so here this is the glass. So you're under, so you're fine, you're okay. Now let's look at 3/8 inch, 10 PSI, I'm sorry, 10 PSI coming from here, and TD is 20. So you're barely sufficient. So you can choose either thickness of glass to be 3/8 inch or a 1/4 inch, half inch for design purposes. You will have for annealed glass, or if you're doing testing, you would if you're working for somebody or you're looking to do tests, you'll be testing for a wide range of pressures and times and come up with curves that look like this. We have seen curves that looks very similar to this, and then those are design charts. So I think glazing at this point, who works, Raghav? You've done testing, right, for glazing? Who's doing? Oh, you're doing? Can you talk about what you're doing? On which glass? And how many laminates? Wearing the glass. And what are the interlayer types? PVB or? 3 types of interlayers. And are they rectangular configurations or? Yeah. Are you simulating? Are you even doing the frames also as part of the fixed boundary conditions? And then you're doing simulations, applying pressure versus blast pressures on them? Or ballistic, you're doing ballistic, impact type. So boundary conditions play a big part on it. When we used to develop models, the contractor used to insist on developing, including all the frames as well, because it can slip quite easily. Slip conditions are hard to simulate, but anyway, those are some of the things in glazing design. Are you designing the glass and then simulating it? Okay. Are you planning to do tests on it also later, or you're planning on? Okay. Oh, you do? Uh-huh. From European standards. And the standoff. These are legacy documents, TM5 1300, and the whole about 40-50 pages of these charts. You can use these charts depending on the type of glass. There may be updated charts also on these. All right, I think for today we'll